Okay, today we're going to take a look at what we call ladder primes. Now, if you've read about or seen or heard about Ackermann numbers, those are the inspiration for these ladder primes. So with ladder primes, what we do, for example, one series or one array of ladder primes goes like this. We have 2, which is the first prime, to the third power, which is the second prime. That's because we have 2 positions indicated by the number 2. The next in the series would be 3, which is the next prime, and that indicates 3 positions, of which we have 3 primes. So in this case, we have 3 as the base, and we have 5, which is the next prime, 7 and the next prime over that, 7 being the exponent for 5, and 5 to the 7th being the exponent for 3. And so continuing the pattern, the next number in the series would be 5 to the 7 to the 11 to the 13th to the 17th power. That is 5 positions, the base, and 4 exponential positions for this following number in the series. And then after that, we have, of course, 7 and a total of 7 positions. Okay, well, that's one version. Come down here a little bit, and we can do this a slightly different way. We start out again with 2 to the third power, 2 being the first prime, 3 being the second prime, and 2 to the third because 2 indicates 2 positions, the base, and 1 exponent. But then, since we use 2 and 3, we move on to the next prime, which is 5. And we have 5 positions. 5, that is, the 5 is the base, and 4 exponent positions, 7, 11, 13, and 17. Well, we've used those primes, so the next prime is 19, and we use a total of 19 positions. 19 is the base, and another 18 primes as the ladder of exponents there, which leads us to 103, since we've used from all the way up to 101. The next prime would be 103, and then we'd have a total of 103 positions, starting with 103 as a base, 107, 109, 113, etc. But we could do things differently yet. For example, we could have 2, and because we have 2 as the first prime, that indicates 2 exponent positions, 3 and 5. Okay, so we use those. So then the next one we go to is 7, and use 7 exponent positions from 11 to 31, and that leaves the next number in the series to be 37, followed by, or with 37 exponential positions. So you see this gets very large very quickly. Now in the case, there's another way we can do this. That is, for example, 2 to the third. That is, we have the base 2, indicates 2 positions, 2 for the base, 3 for the exponent. That equals 8. And for the next element in the array, we skip 8 primes. Skip 8 primes. So we skip 5 to 29, and the next prime is 31. So we have 31 and a total of 31 positions. That is 31 for the base, and 30 prime exponents for the ladder. Okay. And if we say that that number equals to A, then we skip the next A primes and repeat the process. All right, if we take the case of 2 and 2 exponent positions, that gives us 2 to the 3 to the 5, which is the same as 2 to the 243rd, which is a pretty sizable number. Then we skip that many primes and start with the next prime and that many exponent positions. And that's going to be probably an intractable number, probably something we wouldn't be able to calculate. Okay, so, and we could continue on inventing more series that increase in a larger and larger fashion. Okay.